The charge of the sphere is such that its density decreases or increases. So rho sub r is alpha, let's say decreases, so there is more charge at the center. Some decreasing function of r. So that means that now there is most of the charge. That's kind of like, if you remember, Daniel, in gravity, that would be like kind of like saying you're inside of a planet whose density is decreasing, and which is the case for most planets, because the core of most planets are dense at the center, and as they go off, they get less and less density. You see? So it's kind of similar to that. So as we're going out, the density is linearly decreasing until the outer edge of the sphere, there's very little charge. So now what answers would change? Since this one, there's no hole problem, none of the answers at 3 will change, at 4 will change. The only answer that will change is the electric field at r equal to 1 and the flux at r equal to 1. That's it, So then how do you do that? So then you do the Gaussian. Okay. So you want to find out now how much charge is included within radius of 1 meter. So then you say E times 4 pi r squared is equal to Q enclosed over E0. Then rho is defined as dq dv, volume charge density. dq is rho dv. So then you take volume spherical shells, and then dv of a spherical shell is 4 pi r squared dr. Okay, so it's the surface area of the sphere times the thickness. So then you're going to do Q enclosed is going to be the integral of rho dv. Integrate. Rho is going to be the function that I have, r over r, alpha over r. And then dv is going to be the 4 pi r squared dr. So then to find how much charge is enclosed from 0 to all the way to r, then I just integrate 0 to r. And I have E, the 4 pi should cancel this 4 pi. And then you get here 1 over E0. Alpha comes out of the integral. And then the r squared comes down here. And you integrate, r cancels one of the r's. So you integrate r dr from 0 to r. It actually ends up, let's see here. Electric field is alpha over epsilon 0 r squared. And this is just r squared over 2 from 0 to r. Then you just have alpha over E0. So this r squared just cancels, right? So you just have alpha over E0 2. Well, that means the electrical field for that kind of a sphere is just constant inside the sphere. It doesn't increase or it doesn't decrease. But the flux for that will be alpha over 2E0 times 4 pi r squared. So the flux will increase as a square function instead of as a cubic function, right? Remember, for the uniform charge density, it increased as a cubic function. So the flux will increase as a cubic, but the electric field will stay the same. Okay, but now we need to calculate what alpha is, right? The fudge factor. So how do we calculate the fudge factor? We integrate for the total charge of the sphere, integral rho dv from 0 to capital R. So you're using the same rho function that you're given. dv is still 4 pi r squared dr, but now you're integrating over the total sphere to find out what alpha needs to be. So Q total, then you have 0 to R alpha over R 4 pi r squared dr. And then R cancels. Then you have here 4 pi alpha 0 to R and R dr. So then you get Q total is 4 pi alpha, and you have R squared over 2. Right, and then alpha has to be, so now that tells you a constraint on what alpha has to be. So in other words, if you want rho to be alpha over R, alpha needs to be a certain number such that the total charge of the sphere comes out Q total, right? So then this cancels this, and then alpha comes out to be Q total over 2 pi r squared. So that's the fudge factor. Then you put that into here. Over 2 pi r squared. But then you put the E0 and the 2. Oh, okay. So then you get what? Okay, then you get the 1 over 4 pi E0, which is the K, over R squared. Oh, okay. So you see what happened? The electrical field for that sphere just literally starts out at KQ total over R squared. Literally just starts out constant. But when you get to the surface, it's still KQ over R squared. Then it drops as 1 over R squared. And then its flux would look like an R squared function. It would increase as an R squared function, and then we go up, 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 all right, instead of a cubic function. But when you get to the surface, it still should be the same thing, 1130. As long as the total charge is the same, the surface should be 1130, and then it should just go constant like that. So in that kind of a planet, essentially, your gravity would never change inside of that planet. You would always weigh whatever you weigh at the surface of the planet. So essentially what's happening for that is that since it's a steeply decreasing function, it's like this, right? Most of the charge is like right in the middle. So as you're going in, most of the charge contained is still in there. So even though essentially like this, kind of visually it looks like this. Imagine this is the sphere. Even though as new electrical field lines are coming into the, oh, okay, here's how we can visualize this. We can take the sphere and cut it into 3 spheres, one at r equal to 1, one at r equals to 2. 3 subsections. And then we can say, look, the flux is proportional to R squared. You see this from here. So because it's whatever the electric field is times 4 pi R squared. So whatever the flux at R equal to 1, the flux at R equal to 2 should be 4 times the flux at R equal to 1, right? So in other words, if there is 4 field lines coming out of that sphere, if we represent 4 field lines, how many should we represent here? Right, if I double the distance to r equals to 2, the flux should be 4 times. So then I should do 16 field lines there. 1, 2, 3, 4, 5, 6, 7, 8. Let's do 9, 10, 11, 12, 13, 14, 15, 16. You see, that's what it means to say the flux is increasing as a square function. Of course, in real life, there's infinite number of lines that are flowing, but we're representing them by drawing certain select lines. So if I draw 4 here, I draw 16. Now, how many should I draw at r equal to 3? 3 squared is 9. 9 times 4 is 36. Oh my gosh. So then 36, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And then I need 4 more. Okay, no, we still 4 more. 33, 34, 35, 36. Now, if I'm truly representing this, these lines are the ones that go to infinity. I shouldn't introduce new lines there, you see. So it just keep going, keep going, keep going, and then like that, you see. So now, when flux is a measure of the total lines, what's the electrical field a measure of? The lines divided by the area, you see. So I've got 4 lines here distributed over a surface area of radius 1. So what's the electrical field? In other words, it's the number of lines to area ratio. That's kind of how you can visualize electrical field in this setting, right? So you have 4 lines, and then the area is 4 pi times r squared, right? 4 pi 1 squared. So we could say the electrical field is 1 over pi. So don't worry about the exact number, but just say that's a representation of the strength of the electrical field. It's how many lines you're seeing divided by how much surface area that lines are distributed over. So that would be the electrical field at 1. Now, to say that the electrical field was constant in this scenario is to say that the concentration of the field lines didn't change, you see? So what should be the electrical field at 2? How many lines did I have? It was 16, right, that I drew, 16 lines. Divided by 4 pi 2 squared. What is that? So at the r equals 2. And then that one is 4 goes into here, right? 4 goes into here 4 times. And then 4 cancels 1 over pi. Aha, you see? So in other words, 16 lines spread over an area of radius 2 meters represents the same concentration of lines as 4 lines spread over a radius of 1, you see. So therefore, the electrical field strength is the same. Okay, and then what would be the one at the surface? it'd be 36 lines over 4 pi 3 squared, right? And then that's 9 times 4, 36, 1 over pi. Wonderful visual, guys. Very, very good. So you see how the electrical field, what it means to stay the same? The concentration of the lines is staying the same, but not the number of the lines, you see? So now what would be the electrical field value for this at R equals to 2? It'd be K, well, it's just going to be the same thing at the surface, right? KQ over R squared. So that'll just be 10. That's it. So the electrical field is always 10, 10, 10, 10, 10. Even at the center, it's kind of weird. You know, because there are 0 lines at the center, but it's spread over an area of 0. That's kind of weird. There's no 0 lines here. Wait a minute, what are we saying there? For that kind of a planet, even if you're at the center, you still weigh something. It is kind of a weird planet because the density goes to infinity when you're at the center, you know? So it'd be kind of a weird charge density of infinite. Well, it's saying if it's like that, if you can ever find something like that, then yeah, at the center there you would still experience a force. That's a bit weird though, for you to experience a force at the center, because you're right in the middle. There might be a discontinuity. There might be something like this, and then an open hole, and then closed hole. Because it's weird for you to experience an electrical field right at the center. So maybe there should be an open hole here. Like that, like that, like that. Okay, guys, so the other case is the cylinder. So maybe we finish with that. Let's do we already know the equation for the rod at the outside. So cylinders inside. So let's say we happen to have a cylinder with the same exact radius, 3 meters. And now the length of the cylinder is 10 meters. So now let's find let's say the charge distribution. This time, let's say the charge distribution is alpha R. Let's say it's linearly increasing. So what would be the electrical field strength at any point? The outside is still going to be the same equation that we had, 2k lambda over R, remember? The electrical field that we derived for a line charge. So that's for any R greater or same as R. So the only thing that will change is when I go inside of the cylinder. So what is that going to be here when I'm inside? So then it's just going to be E dotted into dA is the Q enclosed over E0. And then this one, remember the dA that we choose, since it's cylindrical symmetry, would be the surface area of this cylinder here. So it'd be 2 pi RL. And then the Q enclosed is rho dV. So dV, you're choosing a bunch of cylindrical shells like this. Right? So then you're integrating the volume charge density over all those cylinders. So alpha R then dV is 2 pi r dr times L. It's the circumference of this circle, 2 pi r, times the thickness, times the length of the cylinder. That's dV. And then you're dividing it by E0. Then integrating 0 to r. And then the 2 pi cancels, the 2 pi cancels, the L cancels, the L cancels. And then you're left with E is equal to alpha comes out of the integral, R comes down on the bottom. And you have integral 0 to r, r squared dr. So I'm doing straight out non-uniform charge density for a cylinder inside the cylinder. So then you're going to get here alpha over RE0, r cubed over 3. And then the r cancels. Let's see, does that work? Alpha. Yeah, alpha r cubed r squared. See this r, which came from the 2 pi RL, that one r comes down and then cancels with one of the r's when you integrate it, after you integrate it, in other words. Okay, so now we have to do the fudge factor again. What should alpha be so that when I integrate over the full cylinder, integral rho dV 0 to r. So alpha r 2 pi r dr L. And then you get here 2 pi alpha L integral of r squared dr, right? R squared dr, 2 pi alpha r. Okay, so then you're going to have q 2 pi alpha L r cubed over 3, right? So now we're going to solve for the fudge factor. Alpha is going to be 3q over 2 pi L r cubed. Okay, then we put that into that fudge factor into here. Then that gives you the electrical field. So you got here alpha is 3q over 2 pi L r cubed. Then we got the 3E0 down here. Then we get r squared. And so then E cancels the E. Okay, remember Q over L was the lambda, the linear charge density, r squared over 2 pi E0. And then you got left with r cubed. Okay. So the electrical field now is squarely increases, not linearly. You see, now it's a square function. Whereas when it's a uniform charge density, it's usually linearly increasing, right? So then let's find out what the electrical field is at 2 meters again, and at 3 meters, and then at 4 meters. So ask the same questions as for the sphere. And what is the flux at 2 meters? What's the flux at 4 meters? 3 meters. And what's the flux at 4 meters? And then we can end with that. Okay, so electrical field is going to be what? Lambda is the charge per unit length. So if it's 10 nanocoulombs, right? And then divided by unit length. So it depends on what the length is. So if it's a 10-meter rod, so with spheres, you don't have to worry about the length of the sphere. But with rods and cylinders, you have to. So divide that by the length of the rod. The 1 over 2 pi E0 I just usually express as 2K, like that. Because remember, 1 over 4 pi is 0. 1 over 4 pi is 0 is K, so 1 over 2 pi is 0 is 2K. So then that's going to be 2 times 10, 9 times 10 to the 9th. So I've taken care of this guy. I've taken care of the K, 2. This is the length. This is the charge. Okay, then you do R squared. So 2 squared over the radius cubed. 18 times 4 over 27. Right? So 9 goes into here twice, 9 goes into here 3 times. 8 over 3. Right, 8 over 3, so then it's going to be what? 2.667 newtons per coulomb. Okay, so now what's the electrical field at the, oh, let's do the flux there. What would be the flux at that point? Then you can simply just go with the electrical field, multiply it by the surface area of a cylinder, right? What would be the surface area of a cylinder with radius 2 meters? So it'd be 2 pi RL, right? 2 pi, this is you're multiplying the circumference times the length. So 2 pi times 2 times 10 meters. Okay, that's the flux at 2 meters. .11 newtons per coulomb times meters squared. Okay, cool. Now, how about at 3 meters? At 3 meters, this equation should get much easier, right? Because at 3 meters, R is equal to big R. And then you can use the outside equation. Then this one cancels this. Then you're just left with the equation that we have, 2K lambda over R. Okay, this one here, 2K lambda over. So once you're at the surface or you're outside, then you just use the outside equation. So the electric field at 3 is going to be 2 times K times lambda. So with lambda, always do the charge over the length. 2 times K lambda, and then divided by R. So 1 over R. That's it for the surface, when you're at the surface. So 10 cancels the 10, this cancels that. 3 goes into 9 3 times. 6 newtons per coulomb. Okay, so you see the electrical field increases as a square function. So at 2 meters, it's still very weak. But by the time you get to 3 meters, from 2 to 3, look how much it increases, because it's a square function, right? So it increases from 2.66 all the way to 6. Okay. Now, what should the flux be? There's 2 ways I can do that. I can do 6 times 2 pi RL, or I could just simply do Q enclosed over E0. I think I'm feeling like a little lazier. I'll just do the Q enclosed over E0. The other way would be 6 times 2 pi R, and R is 3 times L. You see? So with flux, you're a little bit more flexible how you want to do it. With Q enclosed over 0, I just do 10 nanocoulombs over 8.85. Oh, actually, that's the same flux as for the sphere. Right? It doesn't matter. It doesn't matter that, yeah, see, that's a good point. Really, it doesn't matter the shape. As long as I'm at the surface, the electrical field lines is the same as long as the charge is the same. The electric field changes because it's the distribution of that flux lines over the area, right? So this is going to be our famous answer, 1130. That was actually a good thing to see from there. You see the 1130 for the sphere? So whether it's a cylinder, a rod, or anything, as long as I'm on the outside and if it has the same charge, the flux is 1130. .97, I think. So you don't even have to do anything. We already knew that. Okay. Okay, how about at 4 meters? The flux at 4, again, same. Okay, how about the electric field at 4? Well, it drops as 1 over r function, right? So again, what's a quicker way to do it? If it drops as a 1 over r function, so then I take the answer that I got for 6, I multiply this by 3 to get rid of the r, and then I divide by 4. You see? So 6 multiplied by 3 divided by 4. Because I want to find out the electrical field at 4. So here I found the electrical field at 3, and then electrical field at 4 will just be multiply it out, then divide by 4. So electrical field at 4, 4.5 newtons per coulomb. So of course that's different than the electrical field was at 4 meters for the sphere, right? What was the sphere? 5.6625. You see, the flux isn't changing. So you're literally saying, it's kind of like saying there's 1,130 lines at 4 meters, whether you're the sphere or the cylinder. But for the cylinder, it's distributed over a larger area, so the electrical field is weaker, 4.5. You see? But for the sphere, it's distributed over a smaller area, all those lines. So the electrical field is stronger for the sphere. Okay, and right on the money, 3:30, guys. Good, good, good. We finished that chapter, so Monday we start voltage and energy.